Hello everyone, welcome back to our Calculus 2 course this semester. Today I'm gonna start chapter 11. I think it's the last chapter of our course. It's all about sequences and series. And in this video clip, I'm gonna start with the first two sections of chapter 11, section 11.1 and 11.2, an introduction to what is so-called sequence and a series. Okay, so 11.1 is about sequences, and then 11.2 is about series. So I combine those two together. So let's start with 11.1. It's about sequence. So what is a sequence? Sequence is like a list of numbers. Okay, a list of number in a indefinite order. Order means non-stop. So usually people they know a sequence this way. It's just a bunch of numbers. That's all I'm saying. Okay. Use sometimes they use parenthesis. Sometimes they use curly bracket, and then sometimes they indicate the beginning point and the end point. Say a n right here. N start from 1 to infinity. Some other may start from 0 to infinity, okay? Or this, and right? And start from 0 to infinity, okay? Our book sometimes start from counting. This is like the counting index, A1, A2, A3. So all this means what? This is what? A1, A2, A3, A4, A5, all the way to AN, and keep going forever. And this is a sequence, a list of numbers. And if you start from 0, then you have this. A0, A1, A2, A3, all the way to infinity. Okay? Some people start counting from 0, some people start counting from 1. So I show you both. Okay? And this guy, a sequence. And this AN term right here is called the general term. General term. For example, this is my sequence. 2, 4, 6, 8, 10, See? And you can see what this is. What say if I start counting from 1, this is A1 equal to 2, A1 right here, this is A2 equal to 4, A3 is 6, A4 is 8, and A5 is 10, and the general term for this sequence is AN is equal to 2N. Plug it in. A1 is what? 2 times 1 is 1, right? A2 is 2 times 2 is 4, A3 is 2 times 3 is 6, of course on. Okay? General term. Yeah. Okay. Let me give you a couple more examples, and we're gonna move on to some property of sequences. Okay. So the definition is pretty simple, but the math may not be that easy. Sequence what? It's just a list of numbers in definite order. It's just a bunch of numbers forever. So you can have a sequence, right? So 2, 4, 6, 8, you have this? Okay. How about this? 2, 4, 8, 16, 32. You see the rule for the second sequence right here? Keep doubling. Okay? Keep adding 2. This one is what? Keep multiply by 2. Okay. How about this? 1, 1/2, 1/3, 1/4, 1/5, so on and so on. Okay. How about this? 5, 5, 5, 5, 5. Okay. Okay. How about one more? This is a very special one. How about this? 1, 1, 2, 3, 5, 8, 15. Okay. How about this? 1, 1/2, 1/4, 1/8, 1/16, etc. Okay. Okay. So this first sequence right here, you keep adding 2 to get the next term, right? Keep adding a number to get the next term. If you add a constant to get the next term, you learn from pre-calculus. This one called the arithmetic sequence. Arithmetic. Okay. Keep adding a constant. And the general formula, the general term for this first sequence is AN is equal to, if I start counting from 1 and this And so A1 is 2, so this is 2 plus, right? 2 times n minus 1, I think. No, this is 2n. This is the formula. This is A1 plus d times n minus 1. D is a difference. It's 2. And then n minus 1 is count. So this is really 2n. Okay? The second formula right here, this is called the geometric sequence. What is it? Instead of adding 2, you keep multiply by 2. So if you keep multiply by a constant to get to the next term, and this is called the geometric sequence. And the rule for that sequence is an is equal to, and this one right here is, the general formula is this, a1 times r raised to the n minus 1, where a1 is the first term and r is the constant you keep multiplying. So in this case, 2 times 2 to the n minus 1, which is 2 to the n. So 2 to the 1, to the first, to the second, to the third, we have it. Okay? And this one right here, I think is called harmonic. Yeah. And you see the rules, obviously, it says an equal to 1 over n. Okay? And this is all 5, so this is a constant sequence. Constants. Okay? An is equal to 5. All the terms is here. Okay. And this is a special one. This is called the Fibonacci, I think. Check my spelling. Fibonacci sequence. Okay. And the rule is this. You start, the first term is 1, the second term is 1, and starting from the third term, you add the previous 2 terms to get to the next. So 1 plus 1 equal to 2, right? 1 plus 2 equal to 3. 2 plus 3 equal to 5. 3 plus 5 equal to 8, etc. So this is what an, the n term is equal to the sum of the previous 2 terms. So I'm going to write this way. An is equal to an plus, minus, right? Previous term. Minus 2 plus an minus 1. The sum of the previous 2 terms. And as you see, this is another formula to find the sequence. It's not the general term. This is called the recursive formula. Recursive. Okay. The next term we calculate based on the previous terms. Recursive. Okay. So you want to calculate A5, you need to know what A3 and A4. And you want to know A4, you need to know what A2 and A3. You want to know A3, you need to know A1 and A2, etc. Okay. And the last one right here is also a geometric one. Keep multiply by 1/2. Okay. This one is an is equal to 1 over 2 to the n minus 1. See, you start from 1, and this is 1, 2, and it's 1/2, so forth and so on. And you have the general formula for this one as well. And those called the sequences. So I'm showing you a bunch of sequences. This you have right here, and some sequences you got named because you have millions of sequences. Okay, and in general, it's kind of hard to find the general term. For now, basic ones are right here. Of course, you're gonna learn a lot more later on. You see it's in your text, in your homework. Okay, I'll just introduce you some examples of what's called sequence. So what you see in here, a list of numbers, last forever. And we're interested in the end term. And we are interested in the behavior of the end term, of the final term, of the ending behavior, make it that way. Then what if we keep writing down more and more terms of the sequence, what will be the later term, the later term gonna be, okay. So, say for the first sequence right here, 2, 4, 6, 8, and what, 10, 12. So you see what the term getting bigger, right? All right. So if n goes to infinity, what happens? Let's make it that way. So now it's calculus, so I can talk about limit. Okay. In other words, your interest is taking the limit of the general term n when n goes to infinity. See what happens. So let's start with the first one right here. Okay. An is equal to 2 to the n. Okay. If you take the limit of 2n when n goes to infinity, Another word, you're interested in what? The ending behavior of that sequence right here. 2 times infinity is equal to infinity. If the answer is infinity, then you say what? The sequence is divergent. Divergent. Okay? Means what? It's go to infinity. Sometimes it's undefined, and you say divergent as well. This one right here also divergent because limit of what? This an is equal to what? 2 to the n, I think. Okay? Limit of 2 to the n and go to infinity is still equal to infinity. Divergent. What about this one? This general term is an is equal to 1 over n, right? So if you take the limit of 1 over n, when n go to infinity, 1 over infinity is equal to 0. Say what? This one, the sequence is convergent. Convergent means what? It approaches a finite number. Okay? The constant obviously is going to be convergent because it doesn't matter what, the limit of 5 is equal to 5. The ending term is still 5. We keep 5 forever. And this one right here is divergent because what? It gets getting bigger because you keep adding the bigger numbers. You're going to get a bigger numbers. Okay? And the last one right here is convergent because what? You got smaller fraction, eventually the limits go to 0. So the limit of 1 over 2 to the n minus 1 and go to infinity is equal to 0. So this is convergent. Okay? Let me show you another example that shows that the limit is actually undefined. So far in all the examples I gave you on the board, it's either equal to a finite number, or convergent right here, or go to infinity is mean divergent. Let me show you another example. Say this one. 5, negative 5, 5, negative 5, 5, negative 5, da, da, da. So all 5 is just keep alternating the sign from positive to negative, right? So this sequence right here is called the alternating sequence of which you change the sign, and the limits is undefined. Okay. And we write it this way. I think this is a good example. An is equal to negative 1 to the n plus 1 times 5. Okay? So when n equal to 1, you got 1 plus 1 is 2, negative 1 squared. This is just showing the alternating part and then 5, right? So the first term is positive, and then the second term is n equal to 2. So the exponent is negative 1 to the third power is negative 5. Okay? And this limit, negative 1 to the n plus 1 times 5 and go to infinity is undefined. Does not exist. So the limit does not exist. You say what? The sequence is divergent as well. Okay? So by saying divergent, we mean that the ending behavior or the end term, we don't have the end term in here really, but when we take the limit of the general term an, when n go to infinity, either infinity or undefined, and you say that the sequence is divergent. Okay? But if the limit is equal to a finite number, say 0 or 5 any constants, then we say that the sequence is convergent. Okay? So those are basic things that we are talking about sequences for now. Let me show you more. Alright, now some calculation that you may have, I see it's in the book, so let me just copy it down here. What if you have two convergent sequences? Say you got the first sequence an, and by the way, let me write short, okay? An's approach is, say, big A. And that is a short way of writing that limit of an and go to infinity is equal to A, okay? And people is getting lazy, so write this way. I got another sequence, A, Bn, okay? And Bn is approaching B. So we have two convergence sequences. So if you add those two together, you got limit an plus bn. Keep going curly brackets to a parenthesis, right? And go to infinity. The sum of the two sequences is going to be a plus b. Okay, and similarly, if you do subtraction, there's gonna be subtraction here, multiplication. So it's gonna be multiplication here. Okay, and then division, you're gonna have division. So it's A divided by B, right? And what for last one, we require one condition. B need to be non-zero to have this. Okay, I'm cheating a little. It's the AN minus BN. It's AN times BN. This is what AN divided by BN. Okay, so you got A minus B, A times B. That's one is A over B. But see, we divide, we cannot divide by zero, so we have condition that B need to be non-zero. So what we're saying right here, we know two sequences. The first sequence converges to A, the second sequence converges to B. Then we can do the algebra on the two sequences. We multiply the two sequences. It's going to be conversion to M times B. You add, it's going to be A plus B. You subtract, it will be A minus B. If you divide, it's going to be your division, or A divided by B. Excuse me. But keep in mind that the denominator needs to be non-zero. Okay. And then we have something called I think it's called the squeeze theorem. Then. Squeeze. This is E, right? Theorem. We have three sequences. Okay, so we got the sequence AN. We have the sequence BN. And we have the sequence CN. Say we know A and B. We know that what? AN is always smaller than right this way first. AN is going to be going to A, okay? And you know that. Let's make it L then. L is for limit, so L. And then we saw that BN is also go to L. So two sequences converge to the same number. The sequence AN converts to L, sequence BN also converts to L. And if you know that CN is squeezed between A and B, then you know that. Then the sequence CN is also converges to L. So what it's saying in this is, I wanna study about the sequence CN right here. But what I know is what CN is always in between A and B, just like a sandwich. CN is in the middle, and then I know that the two sequences that I know A and B and converges to the same number L, and for sure doesn't matter how weird that middle sequence CN is. Eventually, at the end, it's going to converge to L as well. Okay. Graphically, you guys can think of it this way. Yeah, AN is up here, right? Oh, x-axis and y-axis. Okay. This is the sequence AN. Okay. This is the sequence BN. Which one is bigger? So BN is bigger, so BN is on top. Think of BN as a line right here, and AN as a line right here. Okay. So AN is always bigger than BN. Did I say backward? I'm sorry. BN is always bigger than AN right here. Okay. And CN could be something in the middle. It could be up and down. See what? Okay. But eventually, when A and BN meet at the same point when n go to infinity, then it doesn't matter how naughty CN is. Eventually, it's gonna flat out because it's always squeezed between BN and AN. So this is CN, what we're talking about. And that's why they call it the squeeze theorem. You know that BN go to a number, AN go to a number, and CN is squeezed between BN and AN, so it's got to be going to the same number when n go to infinity. That is the squeeze theorem. Okay. Let's see what else. This is a recall, I think, the geometric sequence, I think, is that what I have? No, not this. We have this, r to the n, okay? R to the n is going to converge to 0 if r is less than 1. So r is negative 0.5, positive 0.5, positive 0.9. So, and then n go to infinity. Okay, then r to the n going to go to 0. And otherwise, it's not going to be go to 0. It's going to go to infinity or negative infinity. One more property that I see the book say. The sequence an is increasing. Just try to introduce you the terminology when you're increasing. If the next term is going to be bigger than the previous term, so the sequence getting bigger and bigger. If an plus 1 is bigger than or equal to an. Okay. And of course, increasing is the other way around. If an plus 1 is less than or equal to an. Okay. So this sequence is increasing. 2, 4, 6, 8. This is increasing. Right? How about this? 1, 1/2, 1/3, 1/4, 1/5. This is decreasing. And the numbers say it all, right? The next sum bigger than the previous sum. This one, the next sum is smaller than the previous sum, so it's decreasing. This is a C, okay? It's not the E, decreasing. Okay? So it's kind of obvious, right? So you want to know that if the sequence is increasing or decreasing, you compare the two consecutive terms, okay, in general. Let me see. Oh, one more concept. Bounded sequence. Talk about bounded sequence. Okay. So we say what? An is bounded above if there exists a number big M such that an is less than or equal to m for all n. What it's saying is this: bounded above means what? All the numbers, all the terms in the sequence is going to be smaller than a constant. Okay? So some sequence is bounded above. Similarly, bounded below means what? This is bounded above, right? Okay. And then you change the word above by the word below, then you have. So let me write down and then before. And similarly, B-O-U bounded below. So same thing is what? An is greater than or equal to some small m for all n. Right? So all the terms is bigger than the number. Okay? And of course, if this is happening, what? Little m less than or equal to an, less than or equal to big M, and say what? This sequence is bounded above and below. Okay? Example. This is the sequence. 2, 4, 6, 8, da da da. This one is not bounded above because it's getting bigger and bigger. You never find a bigger sum, but this is bounded below because an is greater than or equal to 2 for every term, right? So this is like your little m right here all the time. So this is bounded below. You see, all the terms in this sequence are going to be greater than or equal to 2. Or you can have what? Greater than or equal to -5. That would work too, right? So actually you don't have the a fixed little m right here. You can find any number less than 2. And 2 is called the least, the greatest lower bound because the biggest number among all the lower bound. Okay? Alright, how about this one? 1, 1/2, 1/3, 1/4, 1/5. This an is equal to 1 over n. Is that right? This is greater than or equal to 0, less than or equal to 1. Right? All the terms right here are going to be smaller than 1. So this is bounded above by 1, and all the terms are going to be positive. So it's going to be bounded below by 0. This term is bounded above and below. we good? Okay. Some sequence that's that doesn't have a boundary at all. It don't have boundary above or below. Say for example, this one. 0, 1, -1, 2, -2, 3, -3, 4, -4, 5, -5. So what? One term is getting bigger to infinity, another term is getting smaller to -infinity. So it doesn't have the upper bound, doesn't have a lower bound.